Okay. So, still introduction to statistics. This time we're in week 10. It's week 10 because we did week 9. Week 9 was the exam. I know it's not technically week 10, but we just going week 10. That's just what we're going to do. So we are discussing estimating parameters this week. So last week we talked about, or last lecture, we talked about sampling distributions. And we talked about one way to look at parameters last class. And this class, we're going to look at kind of, it'll make sense what we do because this is kind of like the meat of statistics here. This is a really, really important aspect of statistics. And this is kind of like what you see. What we're going to talk about is when they say 50% of people believe blah, 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 right? Or when they say 23% of people have this, or 12% of people like the color red. When they say stuff like that, how do we know that it's 12% of people? Like, how are we getting that number? That's what we're going to talk about today. Who remembers what a parameter is?
Is the parameter of population?
Population is in the definition, but no, it's not a population. But yes, population is in the definition.
It measures the population of a sample.
No, not really.
Of everyone?
No. What is a parameter? We had two things: parameters and statistics. What is a parameter?
Criteria.
What is a statistic?
Criteria.
Say it again, Joyce.
Something like the criteria.
Not really a criteria, no. So a parameter is basically some numerical information about a population, right? And it's really important. Brush up on those first and second week definitions because this is really important. But that's basically what a parameter is. It's information about the population. And statistics are information about the sample, right? Information about a sample. And remember, our entire goal in statistics is to take statistics that we find out and discover parameters. Right? That's our entire goal in statistics, to take statistics and find parameters, turn them into parameters. Right, that is kind of like what lets us. I mean, we want to learn more about populations. That's kind of what we want to do, right? So moving on, we are in the same place that we were last week. We've already discussed collecting data, organizing data, presenting data. Now, here is an important time for you to go back and look at the methods for collecting and organizing data. Right, it's really important because this is kind of bringing us full circle. So you got to go back, look at those methods for doing those things. So that's going to be critical that you go back and you understand the different sampling methods, that you understand the different ways to organize data, how to make a histogram, etc. It's really important, right? And we're still answering that question of now what? Now what do we do? So again, our same analogy. We've been beating this analogy into the mud, right? We're making some kind of soup, some kind of dish, and we want to see, does it need salt? We want to see, does it need this? Does it need that? So what do? Right? We take a spoon out, we taste it, right? And then we do some kind of analysis to see what is it actually telling us about the whole bowl, right? We took a sample, did some kind of analysis of it, and now we're saying, what is it going to tell us about the whole bowl? That's the inferential statistics. Now we're saying, what do we know about the rest of the pot, right, of soup? So when we're talking about parameters and estimating parameters, most times we're actually interested in the population parameters. And I say that to say that we're not really interested in the information about the samples, right? So if I just go out and I collect the sample, I didn't collect the sample so that I could find out information about the 1,000 random people that I asked the question, right? That's not really what I care about. I care about the entire population that I want to study. But because it's not practical for me to go and ask every single member of a population a question, what do? I take a sample. And again, we talked about it last lecture, when we talked about the central limit theorem. We talked about sample statistics, and sampling distributions. Our statistics, at least some of them, serve as point estimates for the information about the population. So when I go out and I collect my information about 1,000 people, the information I collect about them tells me something about the entire population that they represent, right? That's what they did. They tell me about the entire population. Now, if we were to collect multiple different samples, the statistics we gathered, or the information we gathered, would vary from each sample. One way to think about it is, if I went to our class and I did a survey of our class, and then I went to another class and did another survey, and I went to another class and did another survey, all of the classes would have different mean heights, different average weights, different average salaries. All of the classes would have differences between each one. Each of them would be a sample, and each class would be slightly different. Now, one of the things that we want to introduce, one of the ideas we want to introduce, is this idea of what we call a margin of error, right? That's one of the ideas that we want to introduce. This idea of a margin of error. And basically, what our margin of error does is it basically tells us that we're pretty sure about something, about our estimate, but we think it's between this. We're going to give ourselves some leeway, right? So, for example, if I told you all to guess my age, right? Anybody want to take a shot at guessing how old Professor Salam is?
35.
36.
Okay.
35.
Y'all have some guesses.
42.
Oh my jeez, who was that? You get an F. F. You fail. Somebody say 42? Oh my God. I am not 42. But if I told you to guess my age, and I said you can guess in whatever way you want to guess, right? You can guess in whatever way you want to guess, like your answer, but as long as your answer is technically correct. Would you guess an individual age, or would you guess a range of ages, right? Like, would you guess, like somebody had said 35. Would you guess that I'm 35, but you would say maybe something like, I think Professor Salam is about 35, but I would say definitely between 30 and 40. That's something you could say, right? Or if you thought, let me see what else is in there. Somebody said 37. Aaliyah, you get an F too. So if I said, if you were to guess 37, you say, yeah, I think Professor Salam is around 37, but I'll say like a plus or minus 2 years. Plus or minus 2 years on 37 would put me at what? From 35 to 39. And that's kind of your guess, 35 to 39, right? So we're going to talk about how we can get that kind of margin of error when we're doing our guesses about the entire population, right? Does that make sense? Like why we would do something like that? Why we would want a range instead of just an individual value? Does that make sense to everybody?
Yeah. Can you tell us your age though?
Can I tell you how old I am? No, I
Yeah,
cannot.
you guys like hyped up.
Right.
No.
Oh, come on.
You will never know how old I am.
Well,
Nope.
clearly you're
We
not
can look it up.
Aaliyah said 21. Thank you, Aaliyah. You get an A. Aaliyah gets an
Okay,
A.
well, you're 15. You're 15.
Okay, now that's just rude.
That's just creepy.
That is just rude. I'll tell you. I am about 32 plus or minus 20 years.
Okay, so somebody
I guess
was
32.
right, I guess your age.
Plus or minus 20 years. 32 plus or minus 20 years. So that means I'm either between 12 and 52. My age is somewhere between
Okay,
12
that's
and
not cool.
52. All right. So
How old are your kids?
that's our margin of error. And we're going to introduce that idea. How do we actually find that margin of error, right? And how do we actually find that? And before we even get into that, the first thing we want to do, which we kind of already did with our central limit theorem last time, is we want to talk about this idea of variability amongst the different samples that we take. Because again, remember we said that when we take a bunch of different samples, right, to get as close to building a sampling distribution as possible, when we take all of those different samples, all of the values will change. So we want to kind of look at a way to say how much will those values change. So last time, what was the variability measure that we used? What was the variability measure we used for the mean? What was that one called? What do we call that? Do you all remember that one? The standard. No, not the standard deviation, because we were talking about sampling distributions. So it was something we did to the standard deviation, and then we got a new name for it. What was the new name for it?
Standard error mean?
Standard error of the mean. Yes. So that was one way of measuring that variation, to see how was our mean changing from one sample to another sample, right? How was our mean changing? And we saw, like with our elevator example that we did, that as we sample more and more people, right, our samples will have less variation between them. So the larger our samples are, the smaller the variation there'll be between each of our samples, right? And let's look at this example here. Let's say we were to sample 1,000 adults. I think we did this example kind of. If we were to sample 1,000 adults from each state, right? So each state, we take 1,000 adults. Would you all expect that the means of all of their heights would be the same, somewhat different, or very different? So this is actually an example we did last lecture too. What would you all guess?
Somewhat different.
Somewhat different. And that was the answer last time, right? Basically somewhat different. In that when we take that sample of the 1,000 adults, we don't expect every state to have the same exact mean, right? We don't expect that. But like one state might have a mean height of, I don't know, 5'7", while another state has a mean height of 5'7.5", right? There may be some outlier states, like maybe people are really, really tall in Alaska, and maybe people are really, really short in Hawaii. I don't know, right? But there might be some variation, right? But we would generally expect that all of them will be just a little different, right? If not very, very close to the same. So let's look at this example here. Now I'm just gonna read this. Yeah. Cassandra, your face is up here. Can you read this? You're on mute.
Sorry. Young adults hit hard by the recession. A plurality of the public, 41%, believes young adults rather than middle-aged or older adults are having the toughest time in today's economy. An analysis of the government economic data suggests that this perception is correct. The recent indicators on the nation's labor market show a decline in the tough economic times, altering young adults' daily lives, long-term plans. While negative trends in the labor market have been felt most accurately by the youngest workers, many adults in their late 20s and early 30s have felt the impact of the weak economy. Among all 18 to 34-year-olds, fully half, 49%, say they have taken a job they didn't want just to pay the bills, with 24% saying they have taken an unpaid job to gain work experience. And more than 1/3, 35%, say that as a result of the poor economy, they have gone back to school. Their personal lives have also been affected. 31% have postponed either getting married or having a baby. 22% say they have postponed having a baby, and 20% have put off getting married. 1 in 4, 24% say they have moved back in with their parents after living on their own.
So this is the kind of thing that we could see. You see, this is Pew Research, right? That's what this is. It's Pew Research. And this is the kind of thing that we might read in an article somewhere. Like you're reading Washington Post and you read something like this in an article, or you're listening to NPR And they rattle off some numbers like this, right? So first, starting off, it says a plurality of the public. 41% believes young adults rather than middle-aged or older adults are having the toughest time in today's economy. Let me ask you all, were any of you all surveyed for this study here?
No.
No,
Actually not.
I would bet that none of you were, right? That they didn't ask what your opinion was, right? But at the same time, I would also bet that if we did a poll in this class, our numbers probably would not be too far off from that 41% that believes young adults rather than middle-aged adults are having the hardest time today, right? I would bet that our numbers would probably be somewhere decently close to that 41%, right? And we have some other percentages that are in there. So it said 49% say they've taken a job they didn't want to pay bills, right? Were you all asked if you all took a job that you didn't want to pay bills? No. None of you were asked. So how can they say that 49% of the public if they didn't ask every member of the public? Well, they can say that because they've done this inferential statistics. And the other thing that's important, if we look here, like if we were to click this link down here and kind of read the fine print, it kind of details exactly what happened for them to get this data. Can someone else read this for me? Actually, I'll read it because there's parts of this that I kind of want to skip. So this says that the margin of error. So this is information that's on that Pew Research website, right, where they talk about how they actually found this data. So the general public survey is based on telephone interviews conducted December 6th through 19th, 2011, with the nationally representative sample of 2,048 adults ages 18 and older living in the continental United States, including an oversample of 346 adults aged 18 through 34. A total of 769 interviews were completed, with respondents contacting by landline, telephone, and 1,279 with those contacted on their cellular phone. Data are weighted to produce a final sample that is representative of the general population of adults in the continental United States. And I'm going to skip that next sentence. The margin of sampling error is plus or minus 2.9 percentage points for the results based on the total sample and 4.4 percentage points for adults ages 18 through 34 at a 95% confidence interval. So now we need to break that down. So if we go back here, first it says it's the margin of error is 2.9 percentage points for results based on the total sample, right? So if we look back here, what were the information based on the total sample? Well, it said 41% of the public. That's like the total. That's everybody, right? 41% of the total. And that 2.9% margin of error means that we are at 41%, right? Plus or minus 2.9%. Which means 41% is in the middle. We go that way and we take away 2.9%. Or we can go that way and add 2.9%. What's 41 plus 2.9?
43.9.
43.9.
And what's 41 minus 2.9?
39.9.
So these are our actual numbers, right? Y'all said 39.9? That is not correct. Run that number back.
It's 38.1.
Yes. It is 38.1. So what we're saying, right, is that even though they said 41%, what they really mean is that they really mean between
38.
yes, they really mean between 38.1 and 43.9. So they're, and then the last part is, look what it says, at the what? 95% confidence level. So they're saying they are 95% confident, right, that the actual value for the proportion of people that have this belief is between 38.1% and 43.9%, right? They're 95% confident. So, like with my age, you might kind of, like 95% confident might not have any kind of meaning, but if you had to say, give a range that you were 95% confidence that my age was in between those two numbers, what kind of ranges would you all give?
36 and 37.
You're 95% confident I'm between 36 and 37.
Between 30 and 35.
So 95% confident that I'm between 30 and 35. I'll give some information about me if it helps. I have 3 children. My oldest is 7.
How old
was I when I had them?
35.
When I had them, I was between 18 and 27.
That's too big of a gap. We're not
Right.
gonna be able to
It's
figure
almost
it.
right.
You're between 30 and 37.
Between 30 and 37? All y'all wrong. That's what y'all are.
I'ma say
Y'all are
38.
Wrong. WRONG.
No.
Wrong.
We're not wrong.
Yes, y'all
No,
are.
we're not.
Wrong.
34.
Nope.
Done. 34.
Nope. Okay.
Yep.
So if you all were to come up with your guess, right? Well, you were to say,
31 and
I'm 95% confidence between these, y'all would kind of just be going off like, I don't know, random whatevers that you think in your head, right? It wouldn't be like a mathematical. I did some math and I'm 95% confident that you're between these ages. You would just kind of come up with your own, your own opinion too, Tiffany. You said how many degrees? 2 degrees. So, in this case, what we're going to actually go through is the actual way that you can say that you're 95% confident. The actual way that you can say, oh, like let's say you wanted to be more confident. Like let's say 95% wasn't enough. And you were like, I need to be 98% confident. How do you actually give a range where you're 98% confident, 99% confident even, right? You can't necessarily go to 100% confident. At least the 100% confident, like the range of values would just be so big that it would almost be meaningless. So it's like if you were to guess my age and you said, I guess that you're between 0 and 100. I mean, yes, obviously you are correct, but that doesn't really do anything for us. It doesn't tell you anything. So that's kind of what those different ideas. And I only looked at one example, one of the 2 breakdowns they gave us, right, where they said the margin of error was 2.9 percentage points. That's the plus or minus 2.9, right? That's what that's telling us. The margin of error tells us either we go up by 2.9 or down by 2.9, right? And we had a different margin of error for the other sample between 18 and 34, which was 4.4, meaning either we go up 4.4 or down 4.4. And that would give us between 44.6% and 53.4%, right? So that gives us the range that they're confident that the value is between, right? That's what that gives us. All right.
You're 26? Oh my God.
What?
You're 26, Professor?
No, I didn't say that I was 26, LaDanya. Is that LaDanya?
Yes, I was reading an article about you.
Did you
So I'm
Google
trying to
me?
ask you.
Did you Google me? How do you know that that's actually me?
Everyone's becoming all Nancy Drew.
Okay.
Oh my God.
I know.
You are so smart. You are so
All
smart,
right.
but this is
We're recording this class.
okay. I'm sorry.
Let's continue. After we finish, then we can laugh. I'll tell you how old I am. All right. So that's kind of what we're looking at there. Now, one other important thing I want to note, these percentages, right? We call them, yes, we've been dealing with them like percentages, but another thing that we will usually call them is proportions, right? And in a lot of statistics, at least the statistics that is concerned with social or economic situations, and a lot of statistics, we're dealing with proportions, right? What percent of people have this? What percent of people fit in this category? What percent of people fit in that category, etc. Right? That's usually what we're actually concerned with. So we're gonna call them proportions. Go ahead,
so if a question was asked, like, what's the proportion of this and that, your answer would be a percentage.
Yes, because the proportion is a percent. And now it could either be a decimal or a percentage. But yes, that's what we're dealing with. We're dealing with the percentages, right? So the percentages and the proportions are kind of used interchangeably. And a way to think about it is, imagine if we collected some data and we put it all in a histogram, right? We could look at one of those towers, and that would be the proportion of people, like the relative frequency for that tower will be the proportion of people that are fitting in that, or the percentage of people that are in that one particular column, right? So that's the proportions or the percentages. And again, they're very important, because anytime you see any kind of statistics in quotation marks, right, they're always telling you some kind of percent. Like, did you all know that 96% of statistics are made up? Like that kind of thing, you know, where they're telling you some kind of percent. So let's do another example. So here it says, suppose the proportion of American adults who support the expansion of solar energy is P equals 0.88, right? And that's the parameter of interest. That's the parameter that we're concerned with. So the question is a randomly selected adult more or less likely to support the expansion of solar energy?
More likely?
More likely, because the probability or the proportion of people that do support it is 88%. 88% of people support it, right? And this is what I meant. Like, when we're dealing with the proportions, usually we'll just have a decimal, but if you write it as a percent, it's not a big deal. You just have to understand, be able to go back and forth between percentages and decimals. That's something you have to be able to do. So yes, it's more likely, because obviously 88% is bigger than 50%, right? So that would be more likely to support it, right? So the question is, what if we did not have access to, because this is what this said, the proportion of American adults. What if we didn't have access to all American adults, which we don't? If I told you to go out and tell me what all Americans think about something, you wouldn't be able to go out and ask all Americans something. At least definitely not all American adults, right? You wouldn't be able to do that. You probably would not be able to ask more than like 1 million adults something. And I don't even know if I could come up with a way to ask 1 million adults something. Even that would be relatively difficult, right? So since we don't have access to the entire population, right, how can we find out information about the population? Well, we're going to do just like our bowl of soup, right? We're going to do just like our bowl of soup, where we sample from the population, right? And then we use our sample proportion as a point estimate. Right? Again, here's that word coming back up, as a point estimate, right, to guess the unknown population proportion. Now, in this case, before we walk through it, like how exactly we do that, we already know what we're kind of expecting to get out. We already know that. So we have the answer, and now we're going to go through it to see the different ways we could try to get to that answer, right? So that's what we're going to do. Take a sample, right? And then guess, based on the sample that we take, what the information is about the population. So what we need to do,
No question.
What's the question?
For this kind of Is this a question, like, at the top? Is that a question being asked? Or is it just, like...
It's not really a question. I mean, it's just like, what could we do in this case? We want to know what all
like
American adults... Yeah, it's a scenario. We want to know what all American adults feel like. What can we do? So what we're going to do here is kind of like theoretical. It's not like the exact steps, but it's like the general steps that we would do to find that.
So for this scenario, do we just kind of pick like random numbers, or?
No, we're not actually going to work with numbers. You'll see what we do. Like, it'll make sense in a second. Okay. So the first thing that we can do, right, is we're going to sample. And again, we're doing it with replacement, right? Because again, when we do our samples, we want all of our samplings to be independent. And for them all to be independent, we have to sample with replacement. We're going to sample 1,000 adults from the population. And then we're going to record whether they support solar power expansion or not. And then we're going to find the sample proportion. So we're just going to say how many people did we sample in total. We sampled 1,000. Out of those 1,000 people, how many of them supported it? Okay, 200 people supported it. 200 divided by 1,000 gives us our sample proportion, right? So, and then after we do that, we're going to, and I think this is supposed to say class. That's supposed to say class. So after we do that, what we're going to do is we're going to actually make our distribution based on the proportions that everyone, because each of us is doing this individually, right? And we're going to make a distribution based on the numbers that we each get. Right? So we'll have a bunch of samples, a bunch of sample proportions, and then we're going to plot them all out and do what we do. We describe data, make a histogram, that kind of thing, right? So when we do that, this is what we get. And we kind of already introduced this idea when we did the sampling distributions, but last time we did it with the mean, right? We kind of dug into it more with the mean. Now we're kind of digging into it more with the proportions. So inside of this histogram here, it's a sampling distribution of a proportions, right? Inside of that histogram is all of the different samples that we collected. So how many people are in class right now? So it's 28 of us in class right now, right? 28 of us in class. So we would have done theoretically 28 different samples of 1,000 people. We would have found all the different samples. And then let's say when we do that, Aaliyah, her sample has a proportion of, 85%. And Amber's sample has a proportion of 92%. And Celeste's sample has a portion of 82%. And Hermila's sample has a proportion of 88%. Joyce's sample has a proportion of 90%. And LaDanya has a sample of 81%. And we just keep doing that over and over and over again till we build this entire histogram, right? And we can compare all of our different sample proportions. So the question that I have, after we build this, right, now we have a whole lot of data, but again, we don't care about all of the individual samples. That's not what we care about. We want to know about the population. So if this information here was the information we found from all of our different samples, where on this, right, on this histogram, would you guess that the actual population proportion would be? Like, where would you get? Where would you think it would be most likely that it would be? Would it be here in this column? Would the actual proportion be in this column? Would it be in this column, this column, this column, this one, or this one? So we'll do 1, 2, 3, 4, 5, 6, 7. Throw your guess in the chat. Throw it in the chat. 1 through 7. What is your guess? Type it in. Let me see everybody's guesses. 1 through 7. Which of those columns do you think the actual population proportion will be in? So I see some 4s. I need everybody to type in their guess. Which of these columns, right? Which of those you guessed it would be in? So a lot of people are saying 4. Can somebody who said 4, and I see somebody said 3, somebody said 6. Can somebody who said, so I want one person who said 4. So Sarah, it looked like you said 4. So can you tell me why you guessed 4? Sarah, I don't know I don't know how to say your last name, Sarah. I'm sorry. Not
G,
Sarah Bartholomew.
Gladwell.
Say it again, Sarah. Was it Gladkoff? Okay. Sarah? You there? Okay. We'll pick somebody else then. I don't know where Sarah went. Sarah kind of disappeared. Tiffany. I mean, you were the first person that said in the middle. Can you tell me why your guess is that it's in the middle?
I picked it because it's somebody literally, Sarah said it because I picked it because it's the mean.
Because it's
And
the
that's
mean.
not-
So
that's
you
like
think the population proportion will be the mean of all of our different sample proportions?
Yes.
Okay. And it looks like Sarah Bartholomew said 5. Sarah, can you explain why you said 5? And then Cassandra and Amber, you explain why you did 3 and 6. And Joyce, you said 5 as well. If Sarah's reason is not the same as your reason, you can go after that. So Sarah Bartholomew, why'd you say 5?
Honestly, I can't tell you why.
Okay, you just took a guess. Nothing wrong with that.
Yeah.
All right, and Cassandra, why'd you say 3?
I chose 3 because I looked at the total population, I think that is 3,000. And since 4 surpassed that number, I was like, that's beyond the population. And 3 looked like the closest number to that. I don't know.
Okay, interesting.
That was a guess.
Interesting. And Amber, what about you? You just guessed?
I just guessed.
Okay, that's cool. Joyce, what about you?
I just guessed.
Okay, so if we look at this example, right, the numbers on the side are kind of like counting how many people there were. And again, remember what we're doing. We're doing samples from all of us, right? All of us did samples, right? So when all of us do samples and we start putting people into putting different samples that we did into these categories, right? How many of the samples will be in this column here? What it's saying is there's going to be like more than 4,000 of the samples are in that category. So that's what those numbers on the side are saying. But the intuition that if we take all of our samples and then we combine all of that information together and we find what the middle value of all of our samples is, and then we say that's our best guess for what the population value is, that's kind of what we're trying to do here, right? So we're taking everyone's information and we're going to say what's in the middle of everyone's information, and that's probably going to be the population information. So it's like the first step was each of us took a sample. So each of us went out and asked 1,000 people. After each of us go out and ask 1,000 people, then we average all of our things. And guess what? When we average all of our things, it's almost like we did one huge, it's 28 of us, one huge 28,000 person sample, right? And we average it to see what's in the middle of all of our different sample values. And then after that, we say that that is our best guess, right? The middle of the middle of the middle is our best guess for what's the value for the population. All right, so that's what we're doing here. So basically what we've made here, right, is basically a sampling distribution. And in this case, our distribution is symmetric and it's bell-shaped, which is an important note because what's another word that starts with an N that we could call this?
Normal.
Distribution.
Normal, yes. So this is also normal, right? It's bell-shaped, it's symmetric. This looks like a normal distribution, right? And we already answered this question. We're guessing that our actual population value will be somewhere right here in the middle of the middle, right? That's what we're guessing. The mean of all of these proportions will be our actual population value. That's our best guess, right? And if we were to actually look at it on like a more precise graph, we would see that the middle was 0.88. That's what we would see, that the middle was 0.88, which is what we already knew to be the population value. So it's like we checked our answer and it looks correct. Now, the problem is, in this case, we did an actual sampling distribution. That's what we did in this case. And an actual sampling distribution is when you look at every possible sample that you can take out of a population. Hold on, somebody asked a question. Can we get a ticket for saying 4? Sure, tickets for everyone who said 4. There you go, tickets. So, in this case, right, we already knew it, and we did like a sampling distribution in this case. That's basically what we did. Because again, that would be us taking every possible sample out of the population. Every possible way to mix it up. And again, that's like if I took the class and I said, I'm going to break you all into groups. And I made lists of every possible way I could break you all into groups, right? That list of every possible way would basically be like a sampling distribution. So that's what this is, what we did here. But in the real world, we actually usually can't do that. Like, we almost never, like, it's almost impossible. I'm not going to say impossible, right? But we almost never can really do that. But we want to think of the point estimate as coming from some kind of scenario like that. Like in reality, like even with our example, each of us probably wouldn't go out and sample 1,000 people. Maybe like 2 or 3 of us would go out and do this sample, but all 28 of us wouldn't go out and do this sample of 1,000 people. But just theoretically, like in our heads, that's useful for us to see because we can see that the middle of the middle is probably going to be the value for the population. And understanding what we're getting when we do sampling distributions, that's going to help us understand what our point estimates are telling us. That's what that's going to help us do. It's going to help us understand what our point estimates are telling us. So now what we're going to introduce is another aspect of the central limit theorem. Now, just to take it back really quickly, we had already been representing normal distributions in this manner with an n, and then we say the mean, and we say the standard deviation. We had already been representing them like this. Hadn't we already done that? Represented a normal distribution like this. The difference is that when we do a normal distribution, but we're talking about our theoretical sampling distributions, what we do is instead we still keep our mean, and in this case the mean is the mean of all of the different proportions, so we still keep that, but with our standard deviation of all our proportions we instead change it a bit. And what we get, instead of using the standard deviation, we use this thing, and we're going to call this just the standard error. Right, that's what we call it, SE. Right, it's just like all other standard error, but this is a standard error, right, for proportions. I should have put of proportions, but that's okay. Y'all understand what I'm saying. Now, for that standard error for proportions, what we're doing is basically P times 1 minus P divided by N. N is the sample size, right? P is the population proportion, and then we take the square root of all of that. And that's how we get the standard error, which is basically like the standard deviation that we did last time with the central limit theorem. So it's similar, but we just are doing a different calculation when we're dealing with proportions than we're dealing with means. So you need to ask yourself the question, am I dealing with a sampling distribution of means where I'm trying to find the population mean, or am I trying to find the population proportion? If you're trying to find the population proportion, then you do what's on this screen right here. But if you're trying to find the population mean, estimate the population mean, then you need to do what we did in the last section, right? That's what you need to do, what we did in the last section. So that is the only little distinction here, right? It looks like a lot, it's not really a lot. When I put it like this and I just draw what, like, it's the same thing. The only real thing that changed here is this part right here. This is the only thing that's different. Last time, what did we do? Standard deviation divided by the square root of the what was it last time? The standard deviation divided by what? Anybody remember? Last time we said that our standard error of the means was what? The standard deviation of the population divided by what?
What does it mean?
The square root of the sample size. Remember that? That's what we did last time?
Yeah.
This time, we're not doing this. We're going to do this instead. Not this, this, because we're dealing with proportions. So it's just a slightly different transformation that we do. And that's the only thing that changes. A slightly different transformation. This was for standard error of the means. This one is for the standard error of the proportions.
So this equation, this equation for the proportion.
This equation is for the proportions. This is for the standard error for the proportions, right? Of the proportions. I mean, I'm just gonna erase it. I was being lazy a bit. This is the standard error of proportions, right? So this is the standard error of our proportion, and then we had the standard error of the mean before. And this is again going to help us in finding out and estimating the values of the population, the parameters of the population, right? So we don't have to. I'm not gonna. So we kind of talked about it last time. We kind of talked about why it was critical to have. We kind of talked about last time why it was critical to have that divided by the square root of n thing in the bottom. I'm not really gonna go into this one why it's important for us to have that, but just like with the other one, what you'll notice is that our standard error gets smaller as our sample size gets bigger. Our sample size is n, and as n gets bigger and bigger, the standard error will get smaller and smaller. So n is our sample size, p is the proportion. Now another quick.
What did you say?
I'm sorry, go ahead.
I'm so sorry. I just wanted you to repeat what you said. You said once the sample size gets bigger and bigger.
Yes, because we're dividing by n. We divide by the sample size. So because we divide by the sample size, when you divide by a number, if you divide by a bigger and bigger and bigger number, the answer you get is a smaller and smaller and smaller number, right? Yeah, when you divide by a bigger number, you get a smaller number out as your answer.
I see. Okay.
So that's the main point there. We're gonna do some examples. It'll, I think, be a little easier to understand when we do some examples. But yeah, we'll do some examples. Now, just like last time, we do have some conditions that we need to meet for our central limit theorem to be able to work. The first one is we need independence, right? All of our observations have to be independent. And even though we won't always be able to know if they're independent, a couple of things that we can look at is whether or not we use random sampling. So if we did random sampling, we can generally just say that it's independent, or we can say if we're sampling with replacement. So that's one part. But if we're sampling without replacement, then our sample size should be less than 10% of the entire population, right? Because once we go past that 10% number and we're sampling without replacement, we start introducing some bias. So we want to keep our sample size less than 10% of the population if we are sampling without replacement. The other requirement, so the first requirement was independence. The other requirement is our sample size. So when we pick what sample size will work and how big our sample could be, when we did it with the means, the central limit theorem, when we were dealing with the means, what was the requirement for the sample size? The sample size had to be bigger than what? Anybody? Don't none of y'all remember? What did our sample size have to be? And it had to be bigger than what?
But I believe 30.
Yes, very good. You get a ticket. Was that Giselle?
It was.
Yes, you get a ticket. So yes, N had to be bigger than 30. Our sample size had to be bigger than 30 last time for it to be able to work. In this case, the number of expected successes has to be at least 10, and the number of expected failures has to be at least 10. So basically, for whatever it is that we're trying to observe the proportions of, we need to expect at least 10 of each thing that we're trying to observe the proportions of, right? And if we don't already know the population proportions, right, we can assume a value or guess a value, or we can just look at what we're sampling and just look for at least 10 successes and failures, right? So when we just do the sample, we start doing the sample, and we don't stop until we get at least 10 successes and 10 failures, right? So that's what we would want to do. So moving forward to how we find that out, this is the standard error that we did in the previous slide, right? This is what this is. Standard error we did in the previous slide. Right? It's not hard to do. We just need to know P and we need to know N, right? Now, for us to find out what our sample size needs to be, we need a sample size such that N times P is greater than or equal to 10, or N times and N times 1 minus P is greater than or equal to 10. Now, what do those two things mean? For the first one, N is our what? Our sample size. And P is our what? Our proportion. So if I multiply my sample size times my proportion, what am I going to get? So if I say, like, let's look at the class. There's 28 of us in the class. If I say 30% of the class likes the color red, right? If I say that 30% of the class likes the color red, what would be the class size? The sample size would be what? 28. That would be there. So that would be 28.
84%.
Sorry. So this would be 28, which is the class size, times, what is it multiplied by? P is what?
10.
No, we said 30% of the class likes the color red. So what would be our proportion in that case?
30.
Not 30.
3.
Not 3. 30 is on the right track. 0.3, yes.
Oh, okay.
0.3.
Oh, 3. Got it.
I'm gonna put a question mark. Is 0.3 times 28 greater than or equal to 10?
Greater than.
What's 0.3 times 28?
Wait, Professor, can I pause for a second? So then we're always going to multiply by 0.3?
No, you're gonna multiply by whatever the proportion is.
8.4.
It's 8.4. So this equals 8.4, which is not greater than or equal to 10. Right? So Cassandra, no, you're not always gonna multiply by 0.3. In some cases, it was only 0.3 in this case because I said what? 30% of the class like the color red. I could have said 54% of the class like the color red, or 22% of the class like the color red. Right? So yeah, we multiply by whatever the proportion is.
So question, Professor.
when the way you got the 0.3 is because you said 30, so we had to turn that into a decimal, correct?
Yes, because I said 30%. So we can see that if 30% of the class like the color red, our class size would not be big enough to satisfy this requirement, because that would mean only 8.5 of us, so we could round that up to 9 of us like the color red, which is not bigger than 10, right? It's not bigger than 10. On the flip side, for the other requirement, let's just check the other requirement while we're at this same example. For the other one, N is still 28. What does this 1 minus P represent? First, what did we say P was?
Proportion.
Which is what in this case?
0.3.
0.3. What does that 1 minus 0.3 represent? 1 minus P. What does that represent?
The whole 100% of us.
Well, the 100% of us is what? Would just be 1. P we said was what? What did we say P was? The proportion. And P is what in this case? 0.3. What does that P represent?
1 minus 0.3.
Well, 1 minus 0.3, but what does that mean? What is 1 minus 0.3? So in the first side, when we just had 0.3, that was because 30% of us like the color red. But on this side, we have 1 minus 0.3. What is that?
How many
Is that the margin of error?
No. Sarah, you were going to say something?
Is it the opposite of?
It's the opposite, yes.
First,
Remember when we did all our whole probability conversations, right? It's the complement. It's the other side of the event, right? So 0.3% of people, 0.3 people like the color red, and 0.7 people don't like the color red. So it's the opposite. 1 minus 0.3 are the people who don't like the color red. So that's all that is. So basically, we're multiplying our sample size by the number of people who like the color red, by the percentage of people who like the color red, and then we multiply our sample size by the percentage of people who don't like the color red. And when we do that, what do we get? So 28 times 0.7. What's 28 times 0.7?
$19.6.
So we have 19.6 people in the class do not like the color red, and we have 8.4 people in the class that do like the color red, right? So one of these requirements does work out and the other one does not work out. So this one would work because that is bigger than 10, isn't it? But this one is not bigger than 10. So we would need to increase our sample size until we got to a number that would give us at least 10. Like basically we would want a scenario where at least 10 of the people like the color red and at least 10 of the people do not like the color red, right? So that we can have like a good sample size. Does that idea make sense to everybody?
Yes and no. How did you get 0.7?
1 minus 0.3.
Well, let me do that on my calculator.
So isn't that 70%? So I was in the right direction when I said that 1 meant 100% of the people.
Yes, so as I say, you're in the right direction where it is the 100% of the people, but what does this 1 minus 0.3 represent? Yes, the 1 is 100%, but who are we taking away? The 0.3 that we're taking away are the people who like the color red. Exactly. And we're only left with the people who don't like the color red. So we want both of those numbers to be at least 10. That's our second requirement. Both of the numbers have to be at least 10. Now, another thing that's important here, so that's one thing. Another thing that's important here is this part right here. So in most cases, in many cases, you won't actually know what P is, right? You won't actually know what it is. So I have to keep writing in the highlighter. So P is a mystery. And again, P is the population parameter. Once we put the hat on it, it becomes a sample statistic. So we don't know what P is, but we do know what our sample statistic is because we took samples. What we can do in that case is we can substitute in P hat for P. So in our standard error, we use the statistic instead of the population parameter. So our standard error would become this instead. P hat times 1 minus P hat divided by the sample size. So it's basically like we're using our sample information in our standard error because we don't have the population information. Go ahead, Cassandra.
Sorry, I think I missed that whole part. If we don't have the
population proportion, which is P, right? And most times we don't know the population proportion, right? We don't know it, right? When we don't know it, we can substitute in the sample proportion that we found. And in the case that we did a bunch of different samples, so like let's say we did 5 different samples. In the case that we did 5 different samples, we wouldn't just substitute in this. We would take our 5 samples, we would average those 5 sample proportions out and substitute in that. So it's like we're using the best guess for our proportion value in our standard error. So that's kind of what we're doing. So we take the proportion value, the sample statistic, and we're substituting it in for the population proportion. And we can actually do the same thing for the mean. So before we had this thing here, I'm gonna just put this in a little blob right here. We had this is what we were trying to find out, and we had to do divided by square root of n, right? And when I was doing our z-scores, I think somebody corrected me, and I think that was you, Joyce, that was like, Professor, it's not supposed to be S, it's supposed to be a sigma because it's the population standard deviation, right? In this case, you see here that it's the sigma, population standard deviation, but we don't usually know the population standard deviation. So what we can do instead, and a squiggly equal sign means approximately, instead we can use the sample standard deviation. So we can do the exact same thing. It's basically like when we don't know the population value, just use the sample value in its place. Right? That's basically what we're doing. You're using the sample value. Same thing with your z-scores. If you don't know the population standard deviation to find the z-score, you can find the sample standard deviation and use the sample standard deviation for your z-score. So, sometimes we'll have a really small number when we have like our number of successes and our number of failures. And we want to kind of look at what we expect to happen when we have that the number of samples, the number of successes and the number of failures in our sample is small. And in this case, we're looking at stuff where it's like about 50 in what we expect to see. Right? So what I'm going to do, I'm actually going to go over to the picture. Right? So here's a picture here. And this is kind of looking at what happens when we have different sample values. So when we have n equaling 10, right, we can go down, and when n equals 10, or our sample size equals 10, we're looking at what happens as our proportion value changes. So obviously we'll need a different proportion value, but when n equals 10, that's just not enough people. There's not going to be enough people, even when we get down to the 0.9. And what happens when it's not enough people, right? What happens is it makes the data more discrete. So you see how each of these bars is like really segmented and spread out? That's what I mean when we say it makes it more discrete. So it's too spread out. And it also skews what kind of distribution it is, right? And what we can see is that when we get over here to an n equals 250 is almost like the whatchamacallit is gone. It's almost like the ridges are gone, right? It looks almost like a perfect normal distribution for each of these proportion values, right? In general, even though our minimum requirement is that we have 10 successes and 10 failures, even though our minimum requirement is 10 successes and 10 failures, we kind of want to go for a larger sample size. Like in general, I would say you want to use as large a sample size as you can, right? So if you have the opportunity to sample more people, right? You just, yeah, that's just the better. Don't try to go for the bare minimum, right? And it's kind of evident here as we do more samples. One, it squishes down our guess, like makes our guess more accurate, makes the range for our guess more accurate, right? So let's look at this case. We had p equals 0.1. In this case, our range of guesses, it goes from 0 to 0.4. And as we increase our sample size, now it goes from 0 to like 3. Here it goes from 0 to 0.2. Here it goes even smaller from 0 to 0.2. And then we do 250, it's going from like maybe 0.3 to 0.7. So you see, as we did a bigger sample size, the range of our possible guesses is getting smaller. The range of our results is getting smaller. And you can see that for each of these, the range of the results is getting smaller. I think this one is like the most telling, because in the beginning we have a range that goes all the way from 0 to 1, and then we have one that goes from 0.2 to 0.8 as we get a sample size of 25. Then we have even smaller, it's like 0.3 to like 0.7, and that's when we go up to a sample size of 50. And then when we go up to a sample size of 100, we're like in between 0.4 and 0.6. And when we go up to 250, we're even smaller, in between like 0.4 and 0.6, but in the middle of it. So you see how the gap or the spread of our data gets smaller and smaller. As we increase our sample size, we have less and less variability, right? So we want to have as big a sample size as we can, you know, whenever we had those kind of resources. And this is kind of just detailing like what we just talked about. Which basically, you know, the distribution looks more discrete. We get a skewed distribution. If we have larger numbers of successes and failures, we'll get more of a normal distribution. And when they're both large, you know, it'll be a normal distribution, and it will also not be very discrete. The data will be kind of really, really scrunched in. So what we're going to try to do here, let me see, I want us to do an example, but I don't know if that's the example that I want us to do. Okay, so let's just, we're not going to fully do this example, but we're going to discuss it a little bit. So this same idea, we can spread this same idea with the standard error and stuff like that to other statistics. So in this case, we were talking about proportions. The other statistic that we usually will deal with is the mean, right? That's the other statistic that we'll usually deal with, is a mean. So we can extend this idea to the means, and in this little mini example, they did a random sample and they asked how many extracurricular activities they're involved in, right? And they were trying to estimate the average number of extracurricular activities that all the students in the college are interested in, right? So that was the idea here. So that's what they did. They went around, they asked a bunch of people about the, oh no, wait. I think I messed something up in my slides because I changed it a little bit. So I'm sorry, this is a different example. Yeah, I had to go back and change this. So in this example, this is the one I want to do. Sorry. In this example, what we're doing is we're asking college students to estimate the average number of drinks it takes for them to get drunk. That's what we're estimating in this example, not the extracurricular activities. I need to change the last slide. So that's what we're doing. We're sampling 10 students from the population, right, with replacement, and we record the number of drinks it takes for them to get drunk. Then we're going to find the sample means, right, and then we're going to make a distribution. So this is all the data that we got, where we went and did 146 students, and we found how many drinks it took for them to get drunk. We took 10 of the students out of our data here, just the data, the raw data. We took 10 of the students randomly, right? We found the sample mean. The sample mean we got was 5.9. We constructed a sampling distribution, and this is like our point estimate. This is kind of like what we did last time. But when we do the central limit theorem in this case, right, our standard error is what we had last time, which was the sigma over the square root of n, right? So that's our standard error. Now the next thing we're about to do is we're going to actually look at why we need the standard error. So this was the standard error of the mean. So we're going to look at why we actually need the standard error. And again, this is the thing I was saying a second ago, where if we don't know the population value, we're going to use the statistic. Somebody had a question?
Are we using this equation because we know the mean?
So this is, okay, so in the first set of examples we were doing, we were trying to find the population, proportion. In this case, we're trying to find the population mean. So it's just trying to find two different things. So this would be the mean, and the other one is the proportion.
Already though.
Say that one more time.
I thought they already gave the mean.
We're trying to find the population mean. So we don't know what the population mean is. In this case, what we did was we found the mean based on like the data, our little mini sample. But we want to find what the mean is of the whole population of college students. That's what we're trying to find. So I'm just showing that it's similar to what we had before when we're dealing with the means. The only difference in this case is that our standard error is a bit different. The standard error in this case is sigma over the square root of n, which is the same standard error we had in the last lecture notes. So this is another application of the central limit theorem thing that we did last time. And y'all can read through more in detail about everything that it says on here, but we've kind of already talked about all of this stuff that's on this slide here. Now, the conditions are very similar. The only difference is, again, what we talked about last time with our central limit theorem, that n has to be bigger than 30, right? That's the only difference. N has to be bigger than 30. It's not that 10 successes and failures requirement. When we're dealing with the mean, right, we want our sample size to be bigger than 30, or we need it to be normally distributed if it's not bigger than 30. And one more thing, let's say we don't know if the population is normally distributed. We can look at the sample that we took, and usually the sample is going to mirror the population. So if the sample is normally distributed, the population usually will also be normally distributed. So now, this was just a little demonstration showing that we can do this same process, right, for other statistics, and we did it for the mean just now, like the same kind of idea. Now this is kind of like the meat and bone, and this is only going to take us like another 15 more minutes when we look at this confidence interval part, where basically we want to use our standard error to come up with a margin of error where we say we're confident that our value is going to be here. So before we're just looking at how we get to the actual point estimate, right? That's how we get to it. Now we need to say how confident are we that this is the actual answer. So we call the range of possible values that we're guessing, our range for our guess, we call it a confidence interval or a margin of error, right? And again, it's kind of like what we did with the age part. But the example we have here is basically if we're throwing a spear and we want to catch a fish, would you rather use that spear and try to throw the spear at the fish, or would you rather use a net Like, which one would you all rather? Use a net to catch a fish or use a spear to catch a fish?
A net.
A net, because your aim better just be perfect to use a spear to catch a fish. But with a net, you just kind of scoop out the fish. Any of y'all ever caught a chicken before? You know, ever had to catch a chicken? Ain't none of y'all Southern?
I raised chickens.
You raised chickens? Do they like run? Have they ever run from you?
No, they were like encaged.
Oh.
Not in cages, but like on a farm.
Gotcha.
Oh no, I chased them around in the
You
area.
chase them around in a little area? Yeah. Chickens be fast, and the easiest way to catch a chicken is with a net. That's the easiest way, because if you let a chicken get out, that chicken will smoke you. That chicken is fast, right? So we want to use a net. It's the same kind of idea. We want to have a wider range of possible values, because that will make it easier for us to be confident that our answer is correct. That's what it'll do. It'll make it easier for us to be confident that our answer is correct, right? And if we just report our point estimate, right, we're just using the mean of all the proportions or the mean of all the sample means. If we just report that, we're not very likely to be exactly at the population value. We're not very likely, right? But if we report a range, we are much more likely. If we guess a range instead, we are much more likely. So here's an example here where basically what we did, and I'm gonna I'll read the whole thing. It's not that long. So most commercial websites collect data about users' behaviors and use these data to deliver targeted content, recommendations, and ads. To understand whether Americans think their lives line up with how the algorithm-driven classification system categorizes them, Pew Research asked a representative sample of 850 Facebook users how accurately they feel the list of categories Facebook has listed for them on their page of their supposed interest actually represents them and their interest. 67% of the respondents said that the listed categories were accurate. Estimate the true proportion of American Facebook users who think Facebook categorizes their interest accurately. So if we look at this example, a couple of things we can kind of pick out. First, we did a survey. How many people did we survey? 850 people. Of those 850 people, how many people said that they feel like the things were accurate? 67% said they feel like the things were accurate. So there's two things we get from here. One, what's in this example?
850.
Yes, it is 850. Right, that's our sample size. And what is p hat, or the proportion value that we got from here?
67%.
67%, or 0.67. Thank you very much. You get a ticket, Joyce. One ticket for you. All right, so that's kind of the important information we're pulling out of here. But now the question is, what can we do with that, right? Because what do we want to do? We want to actually estimate the true proportion of all Facebook users, of all of them, not just our 850 people sample. Because how many people on Facebook? Millions and millions and millions? A billion? I don't know how many users Facebook has, but it's way more than 850. That I could tell you for sure. So what are we gonna do here? Well, first thing we're gonna do is write down like we just did. Write it down, right? The next thing we need to do is we need to say what confidence interval. Now here it doesn't say what confidence interval we need to use. In general, the confidence interval that we use is a 95% confidence interval. Now, to explain what that 95% confidence interval means mathematically, we already said that that 95% confidence interval means that we are 95% confident that this is the value. But to explain it mathematically, what we mean is, if I draw a sampling distribution, right, and I put P in the middle, or the proportion we're concerned with in the middle, my 95% confidence interval would be from here to here, such that 95% of the values are from there to there. 95% just comes from, I don't know, the industry, just what people say. A part of it is that when we do probability, right, we say that something's unlikely if it's less than 5% likely. Now, in this case, we can choose whatever confidence interval we want. We could say a 50% confidence interval, but I mean, would you really want to take a guess that was only 50-50, like a 50-50 guess? You probably wouldn't want to guess like that, right? Because, I mean, you could be right, you could be wrong, but it probably would not make too much sense to do a guess like that. So when we say 95% confidence interval, what percent is going to be from here to here? The whole thing is 95%. The P is in the middle. What percent is on this side over here? Take that 95% and do what with it? Divided by 2. What's 95 divided by 2? I didn't hear an answer. I heard somebody.
47.5.
47.5. So we have 47.5 on that side, 47.5 on this side. Our value in the middle is what? 50% is right in the middle. Now, what's 50 minus 47.5?
2.5.
2.5. So that's 2.5% on that side. And on this side, what's 50 plus 47.5? 97.5%. So these are our values. We're saying that we want the stuff that's in the middle, between the 2.5% and the 97.5%. And what we're going to do to get that 95% confidence interval, this is where what that 95% confidence interval means. That we're saying it's between 2.5% and 97.5%. It seems like a big range, but it's not actually that big, right? But what it means is we're going to use the z-scores from those values there, right? That's what we're going to use. We're going to use those z-scores. But what I'm going to show you now is just a little thing to make it a lot easier. Can I erase what I just drew right here?
Yes.
All right. I'm going to erase this. And again, I'll be uploading this video on YouTube for you all as well to rewatch for study purposes. So what we can do is we can just use this 1.96 as representative for that 95% confidence interval. We get 1.96 from our z-score table. That's where we get the 1.96, right? The 1.96 is the z-score on one side that gets us to that 95%. So like, when we did it that way, P is here. We had said it goes up to the 97.5, right? 97.5% is 0.9750. 1.96 is the z-score that's associated with that percentage, 0.9750, right? So if you wanted to use a different one, you would need to find the z-score that was associated with it. And notice it's not the z-score associated with 95.955. 0.9500. It's a z-score associated with that 97.5 because it's the middle 95%, not the leftmost 95%. So basically, what we do to get our margin of error is we do the 1.96 times our standard deviation. So margin of error. 1.96 times our standard error of the mean. That's what we need to do.
What's the 1.96 again?
The 1.96 comes from the z-score for that 95% confidence interval. That's what it wants.
So the margin of error is the z-score times
the standard error.
The standard error. Okay.
And this is for the proportions. It's also the same for it's for the proportions, and it's also for, I don't know who that is, but somebody needs to go on mute. So it's for the proportions. It's okay. It's for the proportions, and it's also for the means. If we're doing the population mean, it would be the same, and if we did the population proportion, it would be the same idea, right? That same point estimate plus or minus 1.96 times the standard error. Now, what we need to do is let's actually find our standard error. So how can we find our standard error? First, we need to say, are we trying to find a population proportion or a population mean? What are we trying to find? Population proportion or population mean in this case? So if we look here, it says estimate the true proportion of American Facebook users. So are we trying to find the population proportion or the population mean?
Proportion.
Population proportion. So our standard error for proportions is P times 1 minus P over N. P times 1 minus P over N. Now let's plug in the numbers. Well, here we have P hat, which is the sample statistic, but we need the population statistic, the population parameter, I'm sorry. Do we know the population proportion? No, we don't. That's what we're trying to find, so we don't know it already. So what do we say we do when we don't know the population parameter and we need to find the standard error? What can we substitute in instead?
Estimate.
Say it again.
An estimate.
Not an estimate, no.
But I thought we could use P instead of the P hat. I mean, we can use P hat.
Exactly. That was the question,
P.
Amber. The question was, what are we going to use? And you're right. We're going to use P hat in place of P. You get a ticket, Amber. So we're going to use that 0.67. So we're just going to go. Uh-oh.
What is the P hat again? That's the estimate, right?
One is a sample statistic, and one is a population parameter. So one is a statistic, one's a parameter. The one with the hat on it is a statistic. The one without the hat is a parameter. We're using P hat to estimate P.
Okay.
So we have 0.67 times 1 minus 0.67 divided by 850. And what do we get when we do that out? Anybody? I'm about to pull out my calculator. So do what's underneath the square root sign first, and then you can do the square root. So we're going to do 0.67 times 1 minus 0.67 equals that. Then I'm going to divide it by 850, and I get that number. And then I'm going to do the square root of that number. Shift square root. Answer. This is what I got out. 0.0161. .0161 is what I got out when I did that. And that .0161 is our margin of error. No, not our margin of error. I'm sorry. That .0161 is our standard error. Now we need to find the margin of error. And how do we find the margin of error? By doing the 1.96 times our standard error. So we do 1.96 times our standard error, .0161. And what's that? I got .0316. And that becomes our margin of error. So I'm going to erase this because it's here in the slides. And I mean, well, you'll see it when I erase it. Like, it's just written a little neater. I just wanted you to, sometimes it's hard to see the steps when you just see it all on one side right away. It's hard to see the steps sometimes. So you can see exactly what we did. It's exactly what we did. I mean, the only difference is they said .016 and not .0161. That's the only difference.
Professor, so our answer, .0316, that is what exactly? What's that?
So that .0316 is our margin of error. So
perfect.
This right here is our margin. So when we say the plus or minus, that's what we're talking about. We're saying plus or minus that number right there. That's what we're talking about when we say the plus or minus. Does that make sense?
What is the last thing? It says equals 0.64, 0.70. What is that?
So remember, we do the plus or minus, right? So that's what they did here. They got the 0.67, which is our point estimate. That's p hat, plus or minus the margin of error. So 0.67 plus or minus that. So they did 0.67 minus it, 0.67 plus the margin of error. And what we're saying is that it should be between 0.64 and 0.7. Like, the actual number should be between 0.64 and 0.7. Does that make sense?
Okay, because, yeah. But what was it, plus or minus? What was the amount that it was plus or minus?
0.03. Or 0.031.
Okay. Oh yeah, which was our margin of error. Okay.
Yes, so it's like plus
so
or minus
our final,
that.
So
your final answer could either be 0.67, so you could write your final
right
answer
there,
either like this, 0.67 plus or minus 0.03, or you could write it like that. Or you could also say between, so we could also say between 64 and 70%. All valid ways to report this. So we could say 0.67 plus or minus 0.03. We could say 67%, and then in the footnote we say our margin of error was plus or minus 3%, right? Or we could say between 64 and 70% of people believe blah, 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 right? So those are all valid ways of reporting the answer. Does that make sense, Sarah?
I'm sorry, I have a dumb question.
No such thing.
Yes. Thank you.
No.
I have to go all the way back to we did the math here, the on top in the middle here, 0.67 times 0.33.
Where'd the 0.33 come from?
Yes.
Look what it is here. 1 minus what? P. What's 1
Right.
minus 0.67?
Oh, that's where we got the 0.33.
That's where the
And
0.33
that-
comes from.
And then we divided it by 850
Then we divide it by 850 because 850 is our what? Sample size.
sample size. And that's how we got 0.616.
That's how we got 0.16.
But Professor, no, we have to square root though, right? After we get that
Yes,
in.
I'm sorry. We have to take the square root. We took the square root. We divided by 850, and then we took the square root of the whole thing to get the 0.016.
That was my dumb question. I didn't see where we did the square root.
Yes, so we just did it. Like, yeah, we just did it. I don't know how to say that. We just did it.
Where did we do that? I mean, where's the answer to that?
So the answer is the 0.016. That's the answer.
Okay.
You get
Oh,
something
okay.
totally different when you don't do the square root. You get something different.
But I
Okay.
think, Professor, I'm sorry, I'm not sure. I think her question has a little bit to do with mine, just to make sure we're on the same page. It's like, once we do the 0.67 times the 0.33 divided by 80, whatever you get from doing that, then you square root, and that's how you get the 0.016,
Yes.
correct?
Yes.
Okay.
So you do everything that's inside of there, and then you take the square root of it at the very end. Now, another note that I want to make sure is clear. I want you to make a distinction between the standard error and the margin of error. So the standard error, right, is that thing there, the square root of the p times 1 minus p divided by n. The margin of error, on the other hand, we have to multiply it by that z-score, right? And that z-score comes from our z-table for the 95% number. So just make a distinction. The margin of error is what we do the plus or minus with. We don't do the plus or minus with the standard error. We do it with the margin of error, right? So that's what we're doing. We're doing it with the margin of error, not with the standard error.
Can you point out which one is the standard the standard error on this equation again? Is that that's okay.
Yep.
All right. Got it. Thanks.
So the SE. All right. So we're going to do one last example. So here, just looking at this one, which of the following is correct? Interpretation is confidence interval. We are 95% confident that, and we see that the answer is B. 64% to 67. Well, actually, this should be 70. All of them should be 70. That's a typo on my part. We are 95% confident that 64% to 70% of all American users think Facebook categorizes their interests accurately. That would be the correct interpretation. So this 95% confidence idea, another thing that we could do, instead of multiplying by 1, let's say you don't remember 1.96, you can just multiply by 2. Right, just do 2 times the standard error. 1.96 is very, very close to 2. So you can just multiply by 2 instead of multiplying by 1.96. What that means, the 95% confidence, is basically saying that we're 95% confident, and when we looked at all of these different samples we took, right, only 5% of them did not include the actual population mean. Only 5% of all samples, right, don't actually include the actual population mean, right? And it's kind of like a visual representation. So you can see this red line, this dashed line going straight down the middle is the actual population parameter, and that red line is the only one that did not touch the actual number. It did not include the actual number we're looking for, right? Now, one thing you want to be mindful of and just as a question, in general, do you think you should use a wider interval or a smaller interval? So you can choose 95%, you can choose 50%, you can choose 100%. Obviously, the more confident you are, the wider your interval will be. The less confident you are, the smaller your interval will be. So the question is, which do you think you should use? Should you use a wider interval or a smaller interval?
Wider.
Wider? So, I would say the answer is probably somewhere in the middle. Because if you use too wide of an interval, the thing doesn't have meaning, right? So, if you guess between 0 and 100, that doesn't really have as much meaning as if you guess between 35 and 40, right? So we want to we don't want too small of an interval, right? But we don't want too small of an interval, and we don't want too wide of an interval. There's a little comment. So it says, taking a look at tomorrow's weather, the high temperature will be between 40 below 0 and 200 above. Like, yeah, the weatherman's never going to be wrong with that interval, but that's completely useless, isn't it? It's completely useless to say between 40 below and 200 above. It's completely useless, right? The very last thing I want us to do is I want us to just look at how we can change the confidence interval. So some other confidence intervals people will use 90%, 95%, 98%. Right, those are some other confidence intervals. Again, you draw the picture, put the 50% mark in the middle. Let's say we want to do 75%, right? We draw a line from the outside. The whole thing is 75%. Then we say, okay, let's split that in half. What's 75 divided by 2?
37.5.
Yeah. More money, man.
So we have 37.5 on both sides. And then we just do 50 plus 37.5. What's 50 plus 37.5?
Truth. That's gonna cost you a lot of money if you want the original.
87.5 is what we get when we do 50 plus 37.5. We get 87.5. And then we just turn that into a decimal. 0.8750. And then we find the z-score that corresponds with that percentage. Find the z-score that corresponds with that percentage. And that z-score is the number you're using to represent that confidence interval, right? And that z-star, right? That z-star is what we mean by the z-score. So it's not that hard. You just need your z-tables to look for it. It's similar to what we did before. So you'd be finding what z-score corresponds with 87.5%. The very last thing I want us to look at, I'm just going to show it to you all. The very last thing I want to look at is an example where we're doing it with the mean instead of with a proportion. So here, a random sample of 50 college students were asked how many exclusive relationships they've been in so far. This sample yielded a mean of 3.2 and a standard deviation of 1.74. Estimate the true average number of exclusive relationships using this sample. So we have our sample mean, and we have our sample standard deviation. Our 95% confidence interval is going to be defined in the same way, right? The point estimate, what's the point estimate going to be? Point estimate is the mean, plus or minus, and then this part here will be our what? Notice here we just rounded it. We didn't do 1.96. We just rounded it up to 2. Here will be our margin of error. That's what that'll be there. Our margin of error. And then how do we find it? Well, first we need to find our standard error. But note, when we're dealing with the means, this is our standard error. And this equals what? So let's do it this way. Standard error in this case, when we're dealing with finding a population mean, equals this, which equals what? Sigma over square root of n, which is approximately equal to s over the square root of n. Right, so that's the important note. This is a case where we use the other one. If we're trying to find a mean, we use this. If we're trying to find a population proportion, we use the other one. Right? You just need to ask yourself, am I looking for an average, a population average, or am I looking for a population proportion? Another hint, if you see percentages and stuff in the question, you're probably looking for a population proportion. If you see a mean and a standard deviation, you're probably looking for a population mean, right? And then we just plug those numbers in. Our sample size in this case was 50. That's why it's over the square root of 50, right?
Professor, I'm sorry. Can you say that again, like the little hint you said?
I said if you see a proportion or percentages in the scenario, then it's likely that we're looking for a population proportion. But if you see a mean and a standard deviation in the scenario, it's likely that we're looking for a population average or population mean. So just look at the question. If you see the percentages, it's probably looking for a proportion. If you don't see percentages, it's probably looking for a population mean.
Okay, thank you.
And that's probably, not every single time, it's just a probably situation. Just as like a quick little clue, right? So here we find the standard error, and then the last step is the same. Our point estimate, which is our mean in this case was what? 3.2. Plus or minus our margin of error. Right? So that's what we have. Our mean plus or minus our margin of error. And then we get our interval. So we're saying that the actual average number of exclusive relationships these college students have been in is going to be between 2.7 and 3.7. The actual number will be between those two things, 2.7 and 3.7. And with that, we are done. Yeah.
I have a question.
Yep, Joyce, what's up?
Is the confidence interval has anything to do with the empirical rule?
Yes. Yes, it does. Because if you look at the empirical rule, right? Let me see if I can get a blank. Let's see. Get a blank. So if we look at our empirical rule, right? What's our empirical rule tell us? Well, Joyce, you said it. You gotta tell me what the empirical rule tells us.
It tells us most of the parameters will be within 95%. I forget, I'm trying to look at, I lost the date.
Is it like 60, is it a 65 or something like that? Is that like a number too? Like 95, 65, and 50?
Yes, it is.
Because now it makes a little bit more sense to me. Just bringing up the empirical rule, because it makes a little bit more sense. Because it's like a really clear visual of what you're looking like.
Yes, it is. So empirical rule is what? What's the empirical rule tell us? What are those three numbers? I need y'all to be specific on those three numbers. And so what? What's the empirical rule tell us? What are the three numbers? You're on the right track, but it wasn't 65. It was what?
68%.
68%.
95% and 99.7%.
Yes. So I'm gonna do this.
Yeah.
So the empirical rule told us that between here and here is what percent of the data?
I think that's 99.7%.
This is one standard deviation, so it's going to be the first one.
Oh, right. That's the 68%. And if that's one standard deviation.
Yes. So that's the 68%.
And then the 2 standard deviation is 95%.
And then we have, say it again.
2 standard deviations on both sides, I guess, is 95%.
I'm going to just connect it like this. You said 2 is going to be what?
95%.
And then 3 is what?
99.7.
So if you look at it, it kind of also tells us why we're using the one. Remember I told you all that this wasn't exact. It's a little slightly tiny bit different, like the tiniest of bits different, right? That tiny bit difference is why we're at like 1.96 and not at 2. But you saw how we could estimate 2. So 95% of the data was between what? Within 2 standard deviations of the mean. 95% of the data is within 2 standard deviations of the mean, and that is why we use 2, right, for our 95% confidence interval. And if we wanted to do, say, oh, I see some people put it in the chat too. Thank you, Hermila. I saw you put it in the chat. If we wanted to say a 99.7% confidence, what would we use? Well, we would use 3 because that's 3 standard deviations. These numbers down here, the number of standard deviations is also a z-score, right? So the z-score that marks the end of that middle 95%, the 95% that's in the middle, is 2. The z-score that marks that middle 99.7% is 3, right? So yes, this is the empirical rule. It does have to do with the empirical rule. That's where we're getting those z-scores from, kind of. Any other questions about particularly what we talked about? Because I'm going to stop the recording and then you all can ask questions just about the class or whatever you had questions about. Anybody else have questions about what we did today? Okay, so I'm going to go ahead and stop the recording.